Hello, I'm Adam Elowitz. This is my Lab 5 in Physics 2212, magnetic braking with Faraday's law. So first we're going through the goal of this lab, which is use the data from a magnet falling through a tube of aluminum foil, as seen in the diagram to the right, in order to observe Faraday's law. So key concepts are Faraday's law itself, which states that the induced electromotive force is equal to the change in rate of change in magnetic flux through the cross-sectional loop as it falls through the tube. The Biot-Savart law, which states that the magnetic field in Teslas is equal to mu times Ni over 2 times the radius. Resistance, sorry. Ohm's law, which is voltage equals current times resistance. The magnetic force on a loop, which is the magnetic force equal to current times length of the loop times magnetic field over sine theta. And Newton's second and third laws. There's also that the experimental fall time is equal to 1.592 seconds. The computer model fall time, which is 0.928 seconds. So there is a discrepancy in those, but that will be explained as we go through the lab. So the model assumptions given for this lab are our model slash system is a system is the magnet itself and the aluminum foil, with the magnet modeling a magnetic dipole, and the aluminum foil is slash model is the tube it would fall through. Some assumptions to be made is that air resistance is negligible. The only forces acting on the magnet as it falls are gravity and magnetic forces from the tube, i.e., we'll ignore the magnet if it bumps the tube, air resistance, etc. And our given to the length of the tube is 0.463. Some further givens and data is our, let's say earlier, our length is 0.463, our radius is 0.03 meters, our inner radius is 0.024 meters, our mu from lab 3 is 3.29 amps per squared, our mass of our magnet is 0.025 kilograms, and our average fall time is 1.592 seconds, with our trials and times to find that average time being seen in the table to the right. Pause if you need to. Some checkpoint questions we need to examine before we go into the computational model is, why can we use a ferrous tube, or for example a steel pipe? Why does it have to be aluminum foil or copper? So ferrous tube contains iron, which is strongly magnetic and would create a magnetic pulling force that would greatly disrupt the falling magnet. So it would, instead of the magnet falling slower, it would just stick to the side of the tube. And then what happens to the magnet? How is this compared to a magnet falling in free space without a tube? So the magnet experiences an upwards induced magnetic force, which opposes the force due to gravity, and as a result, it falls slower than it would in a free space without a tube. So here's my glow strip code. Going through this a little bit just briefly, we can see right here we have our basic physical constants, and then we get our graph set up. To create our tube, we inserted in our measured values seen earlier, and then this section and for most of this stayed the same. Then we edited our bar magnet to give it our mass and our mu from lab 3. So we visualize that and then calculate the field of our bar magnet using our Faraday's law and our given equations. We then calculated the flux and simulated the it falling through the loop in order to simulate the force in the loop and display, as you'll see in a minute, the currents, induced currents in the tube as it falls. Then finally, we calculate our Fnet and we print the time it takes for the tube to fall. Feel free to pause if you have any questions about this, and my code is linked in the bio. So here, right here, we can see our velocity versus time graph. This blue and red region right here simulates the currents that are induced as the magnet falls. And right here is my graph showing how the velocity greatly increases in the negative direction, then it decelerates, and then it falls out of the tube and increases again. So this period right here can be considered where the opposing force is really kicking in and slowing the acceleration. To interpret this in simulation, so the intensity of the color in the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current and which to counterclockwise? How do you know? So we know that red corresponds to counterclockwise and blue corresponds to clockwise, which is due to Lenz's law. And so the reason why we know that Lenz's law is what connects to this is because by examining a magnet falling into a field, we know that the direction of the electric current induced in the conductor is such that the field is created by the induced current opposes the change of the initial magnetic field. So one of them, the upper one, must be the clockwise current, and the opposing one is red, which is counterclockwise, as it opposes the initial current. What happens to the dynamics of the system when you flip the magnet around? Observation-wise, nothing will really change, but our current's direction would flip. How does the total time in tube of your real-world system compare to that of your computational model? How may our computational model be made more accurate? What makes it be more accurate is because we observed that while falling, the magnet did bump into the side of the tube several times, even when redoing trials, as well as air resistance playing a factor. Some human error might be accounted for as well to make it more accurate. So accounting for these extra forces and outliers variables would help make our computational model more accurate. And what does shape the velocity versus time plot tell you about the force acting on the magnet? As touched on earlier, it shows how the forces are initially unbalanced, i.e. there's acceleration, before leveling out. No acceleration means both forces are going to be equal. Some questions to consider. What if the resistivity of the conductor was reduced as close as possible to zero? How will this impact the dynamics of the falling magnet? The main thing is the forces pushing the magnet up will greatly increase and stop the falling of the magnet entirely. Finally, what if holes or slots were cut into the tube? How would this affect the ring current in your model? So it would disrupt the flow of current, and as a result, the force pushing the magnet up would decrease due to the current decreasing as a result of the cuts disrupting it. Thank you so much and have a great day.